we know that the eigenvalues of this Hamiltonian here, they are degenerate, and the eigenspaces carry irreps of SU2. We say now irreps of SU2 with dimensions 2L plus 1. And actually the degeneracy was a bit higher, but we come back to that in a minute. So let's just look at these eigenspaces that carry irreps of SU2. And now if we just add this factor here trivially, then we just double the multiplicities of everything. So now we have 4L plus 2 dimensional spaces. If we really add this spin-orbit coupling now, I don't write down a Hamiltonian, some Hamiltonian which couples these two factors here, and a Hamiltonian which, say, is still SU2 invariant, so like the Hamiltonian before, then what would we expect in this case? Now we have to look at this product representation of SU2, and the expectation is that we can just write this as a direct sum of some SU2 irreps, and then the eigenspaces would correspond, for each irrep we would expect an eigenvalue. We will learn much more about irreps of SU2 later, and we will see that this tensor product here can be decomposed in a 2L dimensional and a 2L plus 2 dimensional irrep. At least that's true for L greater than 0. For L equals 0, it's different, because for L equals 0, here we have a one-dimensional, actually the trivial representation of SU2, and then trivial representation times two-dimensional representation is just a two-dimensional representation. So that's a special case of the line above. And now remember that actually there were a couple of these which corresponded to the same eigenvalue of the original Hamiltonian. So let's look at an example. Let's say we don't show this yet. Let's say that we look at the case n equals 2, and then we had L 0 and L equal to 1 as the two possibilities. So we start here with a gamma 1 for the L equals 0, and let's say a gamma 3 for the L equals 1. And now we have to tensor each of them with a gamma 2. So there's a gamma 2 here and a gamma 2 here. Maybe let's emphasize this tensor product and then a direct sum. And now we decompose each of these. So from the first term we just get 1 gamma 2, and from the second term we get one more gamma 2 and a gamma 4. Okay, so we would expect that all these states which lived here, which all had the same energy for the original Hamiltonian, would now split into 3 states with possibly different energies. Nature is still a bit more complicated. There is still an accidental degeneracy here, so these two come with the same energy. And then the picture, which I didn't want to show too early, looks like this. So we have all these states with n equals 2, L equals 0 or 1, and then this is the spin 1/2, the spin part, with one energy, and it splits into 2 energies here. on the right hand side. So that's what is known as the fine structure, including the spin orbit coupling term. And now if you see these funny symbols here, these are spectroscopic symbols, they translate to what we do here in representation theory. So this, let's say this 2, which you see here everywhere at the top left, that's just this 2 here, the n equals 2. Now the L is translated to some funny letters. So this L equals 0, L equals 0 is called an s orbital. So that's the s here. And the L equals 1 is called a p orbital. So that's the p here. And the numbers at the bottom right, they label the SU2 irreps, which we have here on the right hand side of our equation, but you don't label them by the dimension, but again by a number, so that the dimension is twice that number plus 1 as we had it up here. So instead of this L quantum number here, we introduce, say, some quantum number J, and then we have the dimension of the irrep. So dimension of gamma j is 2j plus 1. So this j here in this case, in the 2, in the case when the dimension is 2, the j is 1/2, and here the j is 3/2, and that's the number you see here. You don't have to know how to label these things, but I just want to point out that this is actually labeling of some irreps here.